Okay, this is DC Motors Part 2, Lesson 28. This little diagram is from Lesson 27, so if you want to go pause it, grab that piece of paper. Just want to make sure that we have these terms down before we keep moving on with our motor, right? So the first, we'll start and kind of work our way around. First one is the commutator, right? This is what allows it to keep spinning. Allows it to keep spinning in the same direction because we have a Lorentz force being developed, and it would no longer be able to keep spinning. It would just kind of go back and forth if we didn't change how the current was flowing through. Then we have, this is the poles, right? If you think of this as the north and the south or vice versa, right? It is not moving. The magnetic field stays the same, right? Magnetic field is a constant still, right? And it's sending the magnetic field lines across this motor. And that's how the Lorentz force is happening, right? The Lorentz force is coming from a current that has an electromagnetic field when it's interacting with an existing magnetic field. So here's the magnetic field. And sometimes it's called the field windings because oftentimes rather than just using a permanent magnet, we'll use another electromagnet from a different source that's going to create a magnetic field B, right? It still needs a B. Right? It still needs a B magnetic field. That gets wrapped up inside of the machine constant, kV, right? kV equals machine constant. If you don't remember that, it's on the equation sheet, kV, right? And that B is a part of it. And these are the armature windings. And this is what current is flowing through. What current flows through, and then also what is spinning. And so it's the current that's flowing, but then it's spinning, and the spinning is coming from the Lorentz force. And everything that's spinning together is called the rotor, right? It's what's rotating. So both the armature windings and the commutators are a part of the spinning part. The stator is what stays the same. It's stationary, and so these poles are a part of the stator. So I'll put in yellow, the rotor is spinning, and then in green, these poles and field windings are a part of the stator. The brushes as well are a part of the stator. They're not moving. And armature windings, they are spinning, right? And so that's just the function of what's going on inside of the motor. Power flow diagram, we have a power in and a power out. This top one is just telling us that we have an electrical power coming into a circuit, right, with a V voltage, right, across it. It has electrical losses, P electrical loss equals I squared R, right? It's not perfect. There's some electrons that don't make it there, but then it comes here, and this is just a diagram of a motor that's spinning, and it's telling us that it's spinning right here, and here's the torque of the load. Think, I keep saying a power drill, but any motor that is an electric motor that spins. And it's telling us that this whole thing has a P out, right, that is going toward my drill, if you will, but then there's friction along the way inside of the motor. And so this force being developed inside from the electrical to the mechanical. So that's what's right here. Inside my power flow diagram, that right there is where the power is developed from the Lorentz force. So there's these equations. And then we have an input power and an output power, and those can be related with efficiency, right? Efficiency is P out over P in. We lose some stuff along the way. Here's the omega. That's the rotational speed of the motor, right? And that power developed is dependent upon the E induced is dependent upon a rotational speed. Here's my E induced is EA. And sometimes we'll ignore rotational losses. If we say ignore rotational losses, it's saying ignore this. And if we say an unloaded motor, right, I just need to spin it. I'm not putting any screw on. I'm just spinning my motor. The only thing holding it back is friction. And that would be the T load, would be 0 in an unloaded situation. In fact, I'll have you just write it down. Unloaded, T load equals 0. No rotational losses or frictionless is where T loss equals 0. That'd be 0 watts. No, not 0 watts. Newton meters. Newton meters, Newton meters, Newton meters. Another way to say it, the unload means that the P out equals 0 watts, and this would be the P mechanical loss equals 0 watts. So sometimes we'll be given those scenarios. Frictionless is purely hypothetical, or just if frictional losses are negligible, right? Then we could assume they're like 0. So in a real motor, this is just saying that we could increase the efficiency of the motor by adding more windings or by adding more poles, right? Add more poles can increase the efficiency of our system by raising the field strength B. We add more poles instead of just a north and a south. We have several north and south. So right here, we have these more magnets. Usually it has to go by pairs, right? North and south. So like 2, 4, and 6, we can increase the number of poles. This right here, if you want to read it, it's a discussion of the fact that whenever I have my little circuit, right? Here's my initial circuit. Well, if I have no movement, then I have no back EMF. No omega means there's no EA, right? And if there's no EA, then it's not opposing it, right? That this EA would be a dependent voltage source dependent upon some sort of angular velocity, rotational speed, angular velocity, same thing, omega. And so all that's stopping it is R. Well, whenever this EA is 0, then I have a high current initially, right? And so what we'll do is we'll use more resistors to keep the current low and not overwhelming the wires, burning them up, melting them. Use more resistors to keep current low. Current being at the speed that we need. So we'll use, right here, they have like a starting and a resistor at the start. And then once the motor's fully running, then we can use a short, and it bypasses this where that starting resistor is dead, because the back EMF has been developed, that EA has been developed. So you can even put more in, and here's kind of like this pivot arm is moving through where there's more resistors, and then as it starts, it has less and less resistors until it just touches the circuit, right, with less resistors. Okay, we do a problem next.